this tells you what element you're talking about. This is the abbreviation, the official abbreviation for these different elements. Potassium is K, it's not a P. Phosphorus is P. That's why potassium can't be. Sulfur, etc. And right now what we want to look at is, what is this number? Where does this number come from? So you've got three really critical pieces of information on your periodic table. And if you were to look at chlorine and just simplify it, we got chlorine right here. We've got the atomic number 17, and we have a number like this. I believe this is what is on your periodic table. 35.45. This one, 35.453. It's just carried out to a few more significant figure, one more significant figure. But the periodic table I've given you has it to 2 decimal places. This is the average atomic mass for chlorine. Where does that come from? All right, so to understand where that number comes from and how to calculate it, that's what we're going to do right now. Figure out how to calculate that number. You need to understand what isotopes are. Isotopes of the same element have identical chemical properties. They differ in atomic mass. Difference between atomic mass and atomic number. Well, I forget that. I don't know what. This is a little confusing. They differ in atomic mass. They don't differ in atomic number. So I think that was stated a little bit ambiguously there, or could lead to some misunderstanding. So let's take a look at it. Chlorine, you go to the HEB and buy a bottle of Clorox bleach. It has sodium hypochlorite in it. It has chlorine in it, an oxidizing agent. Well, what are the chlorine atoms in that bottle? There are 2 kinds of chlorine atoms. Any chlorine atom is going to have an atomic number 17. I've told you that's the most characteristic number of an element. How many protons are in its nucleus? If there are 17 protons in the nucleus, it's some form of chlorine. But there is chlorine 37 and chlorine 35 isotopes in nature, occurring naturally in our universe, are 2 different kinds of chlorine, particularly on the Earth here. These ratios of these might be a little bit different somewhere else, in the middle of the sun or whatever. But you can see that chlorine 35 has 20 neutrons, and chlorine 37. I'm saying one thing and working on a different one. So you subtract the atomic number from the mass number, and you get the number of neutrons. Chlorine 35 has 18 neutrons. So these are 2 atoms of the same element. They have the same number of protons in the nucleus, but they have a different number of neutrons. So chlorine has 2 different isotopes. This would be called chlorine 37, and this would be called chlorine 35. So when we refer to an isotope of an element, we just say the name of the element and the mass number. We're talking about a particular isotope. All right? We don't have to include this number in this name right here because, why? From the periodic table, the atomic number is obvious, 17. But the mass number is not obvious. if I'm talking about a particular isotope. So chlorine has two different isotopes. All right, now the next sticky wicket here is that it doesn't just turn out in nature that half of them are chlorine 35 and half of them are chlorine 37. How much of each is there? I don't know why. It almost seems haphazard. They're just there in different quantities. If you go from one element to another element to another element, you can't predict what percent, at least I don't know how to predict what is going to be the amount of this versus this occurring in nature. That's what we refer to as the natural abundance. What is the natural abundance of this isotope versus this isotope? I'm trying to think of an analogy here. If it was 50-50, in other words, if it turned out in nature just by chance, half of them were this and half of them were this, the average weight of a chlorine atom would be the average of these two, right? We just add up the weight of this one divided by 2, we'd have the average. So something like 37 plus 35 is 72, divided by 2, 36 would be the average mass of a chlorine atom. All right, this one's heavy, this one's light. If they were in a 50-50 mixture, the average would be right in the middle. Well, it turns out they're not 50-50. So I think the next slide shows us the relative abundances here. Chlorine 35 has a relative abundance of 75.77%. We're going to look at this very accurately here. Chlorine 37 is 24.23%. Trying to move around to get some space here. So we have, let's put the heavy one on top. Let's keep it. There is 24.23% is chlorine 30. Excuse me, heavier one on top. So 24.23% is chlorine 37. 75.77% is chlorine 35. So there's about, the previous slide said, about a 3-to-1 ratio. There's about, if you rounded that off to 25, rounded this off to 75, you could see this is 3 times more this isotope than that isotope occurring in nature. This is the natural abundance. So you go home, you got your Clorox bleach, you're taking it home. See, now you can think at a very much higher level about your your Clorox bleach. I've got chlorine atoms in here. 75% of them are chlorine 35, and 25% of them are chlorine 37. That's what's in that bottle. 2 different kinds of chlorine atoms. Wherever you find chlorine, you put salt on your food. 75% of the chlorine coming out of the salt shaker is this chlorine. And 25% of it is that chlorine. You follow me? This is just the way it is. Wherever you find chlorine, you go swimming down in the ocean, and it's salty. It's got all kind of chlorides in it. 75% of those chloride ions are this one, and 25% are that one. So then we said, well, what is the average weight of a chlorine atom? If I'm going to go in and do a reaction, and I'm going to use chlorine in the reaction, what is the average weight of those chlorine atoms? So we determine that based on this relative abundance. So let's just go through the mechanics of this. First thing you want to do is convert this into a decimal. Percent means per 100. That's what percent means. 24.23 per 100. If I had 100 chloride atoms, 24.23 of them would be chlorine 37. So that gets me to just moving the decimal point over 2 places. 75.77 per 100 is 7577. And then what you do, I'll slide back over here, you ask yourself the question, what does a chlorine 37 weigh? It weighs 1 atom. It weighs 36.94 atomic mass units. So I'm going to take that number times 36.94 atomic mass units. And what does a chlorine 35 weigh? 34.97 atomic mass units. Okay, now take out your calculators. Yeah? Okay, those would just be that come from a table of masses of these isotopes. Okay? Yeah, this would always be given to you. Yeah.
After you do all that math, when you add it up, when you round, how many places?
Okay, let's get there. Okay, let's get there. Let's take it one step at a time. Let's do the calculation. That's good that you're that far ahead. But let's do that calculation right now. And I would, okay, that's a good question. Let's take the first one, and I would round it off to 4 significant figures. Every one of those numbers has 4 significant figures in it. Where do you get that?
On the over, if you go over, you flip the second set of numbers.
Yeah. Here's 35. It's 34.97.
You have 35 on the bottom.
Thank you. Thank you. I did flip them. 34.97. So what's this one up here? 0.94?
Yes.
Okay. Very good. Good. Are we there? Because they had them, I should have just kept them in the order they had them. Yeah, round it off to 4 significant figures. You're doing a multiplication, and each of these has 4 significant figures in it.
Is the mass always going to be the same for the isotopes?
You mean like chlorine 35? Is it always going to be? Yeah, it should always be that.
34 and 34.
Yeah.
So if they're not given, would you be able to assume that would be its complement? Or are they always going to be given?
They should be given to you. If you were trying to do an element that you didn't know, does anybody have a Band-Aid? Anybody come carry around a Band-Aid with them? I just had a little scrape here, and I just scraped it again. So, okay. So let's do the first one. 0.2. Do I have them? I got the abundances right. All right, everything's right now. Times 36.94. So I would round this one maybe off to 2 decimal places. 8.95. Yeah, that'd be good. I mean, technically it's 8.951. 0.7577 times 34.97. So 26.50. I got 26.496769. I'm going to round that off to 26.50. And you add all of that up. And I would remember when you add numbers, you cut them off to the level you have decimal places for each one of them. So this becomes 35.45. Now look at your periodic table. Your periodic table. What number you got on there? 35.45. That is the average atomic mass of a chlorine atom. Will you find a chlorine atom that mass? No. No, you won't. For every 4 atoms you find, 3 of them will have this mass, and 1 of them will have that mass. And they will average this mass. You follow me? You can't even find a chlorine atom with that mass, but that is the average atomic mass of chlorine atoms. You're never going to have 4 chlorine atoms. You're going to have 4 million. And when you average their weights, their masses, you'll come up with that number right there. Yeah.
So are you given the 75.77%?
Yeah, you're given all of this stuff. How do we determine that? There's something called a GC mass spectrometer. And what they basically do is they would run chlorine through a gas chromatograph and separate them, and then they would run them through they'd probably ionize them a little bit and run them through a